Hi, are you planning to master Amazon EKS service or just getting started to learn containers and Kubernetes? If the answer is yes, you're in the right place. This is a multi-part Amazon EKS deep dive series where we will cover various aspects of running workloads on Amazon EKS. Let's get started. Let's examine the quantified performance results from our comprehensive testing, starting with node lifecycle operations. We used Carpenter to launch 100,000 Amazon EC2 instances with a combination of node pools and instance types. This massive provisioning operation completed in 50 minutes, achieving a sustained rate of 2,000 ready nodes joining the cluster per minute. We then exercised drift operations to update all nodes to a new AMI, simulating a common day 2 operation that customers perform regularly. Carpenter successfully drifted the entire 100,000 node cluster in approximately 4 hours while respecting node disruption budgets throughout the process. This demonstrates that even complex operational procedures can be performed reliably at ultra scale. Finally, we validated scale-down operations by terminating all 100,000 nodes, which Carpenter completed in 70 minutes. These results demonstrate that the fundamental node lifecycle operations, provisioning, updating, and terminating, all work reliably and efficiently at 100,000 node scale. The AP server and a database performance results demonstrate the effectiveness of our architectural innovations. Throughout our testing with various workload scenarios, the cluster maintained more than 10 million Kubernetes objects, including 100,000 nodes and 900,000 pods. The aggregate etcd database size across all partitions reached 32 gigabytes, validating our enhanced database scaling capabilities. API performance remained consistently excellent throughout testing. The P99 AP latencies stayed well within Kubernetes SLO targets of 1 second for gets and writes and 30 seconds for list operations. Even under high load with massive workload churn, the cluster served high read and write throughput without failures. The Kubernetes scheduler consistently delivered throughput of up to 500 pods per second, even at 100,000 node scale. Cluster controllers maintained low work queue depths throughout testing, indicating that they could keep up with incoming operations without building backlogs. These results validate that our controller optimizations and API server enhancements work effectively at ultra scale. Resiliency testing validates that ultra scale clusters can handle the operational challenges that become more likely as system size increases. We induced health degradations across 1,000 nodes and measured the time required for EKS node monitoring agent to detect and mark them as unhealthy, and for Carpenter to perform node auto repair by replacing them with healthy nodes. The results were impressive. All 1,000 degraded nodes were replaced with healthy new nodes in under 5 minutes. This demonstrates that even significant infrastructure failures can be detected and remediated quickly at ultra scale. We also tested DNS performance under extreme load by inducing cluster DNS queries at 1.5 million queries per second. The EKS core DNS autoscaler responded by scaling deployment replicas to 4,000 instances. Even under this massive query load, the P99 query latency remained below 1 second, ensuring that DNS resolution doesn't become a bottleneck for application performance. These resiliency tests validate that ultra-scale EKS clusters can handle both infrastructure failures and extreme load scenarios while maintaining operational stability. The ultimate validation of ultra-scale EKS comes from real-world customer implementations and internal usage at Amazon. Anthropic, the company behind the Claude family of foundation models, operates some of the largest EKS clusters in production today using ultra-scale capabilities. Anthropic's implementation showcases the power of heterogeneous compute optimization. They leverage AWS Trainium chips for training efficiency, NVIDIA GPUs for specific inference workloads, and Graviton processors for supporting services, all orchestrated within the same ultra-scale cluster. This mixed environment requires sophisticated orchestration that optimizes resource allocation across different compute types. The performance improvements are quantifiable and significant. Anthropic has achieved API latency improvements ranging from 35% to consistently above 90%, enabling faster iteration on model development and more efficient user serving. Internally, Amazon's Artificial General Intelligence AGI team uses ultra-scale EKS for building and operating the Nova family of foundation models. These represent some of the most advanced AI systems we've developed, involving massive training jobs with thousands of nodes running complex multi-stage workflows. This internal usage provides continuous feedback that helps us improve the platform. While EKS Ultrascale provides unprecedented capabilities, successful implementation requires careful planning and consideration of several key factors. Ultrascale deployments are fundamentally different from traditional container deployments, and many conventional approaches need to be rethought. Let me guide you through the critical considerations for success. Network architecture design is absolutely critical for ultra-scale success. Traditional networking approaches that work fine for smaller clusters can become bottlenecks at 100,000 node scale. You need to carefully plan your VPC design, subnet allocation, and traffic patterns to ensure optimal performance. This includes considerations for east-west traffic between nodes, north-south traffic to external services, and the massive scale of network endpoints that need to be managed. Storage and data management complexity increases significantly at ultra scale. You're not just dealing with more storage, you're dealing with fundamentally different access patterns, consistency requirements, and performance characteristics. This includes persistent volume management, data locality optimization, and backup and recovery strategies that can handle petabyte scale datasets. Monitoring and observability require scale appropriate approaches. Traditional monitoring tools and techniques simply don't work when you're managing hundreds of thousands of containers across 100,000 nodes. You need intelligent sampling, aggregation strategies, and automated anomaly detection that can surface critical issues without overwhelming your operations teams. Finally, operational procedures must be designed for automation at scale. Manual intervention becomes impossible when managing ultra-scale deployments, so every operational procedure must be automated, tested, and designed to handle the unique failure modes that emerge at this scale. As we conclude this presentation, I want to emphasize that 100,000 node support is just the beginning of our journey in ultra-scale container orchestration. The innovations are shared today represent a foundation for even more ambitious capabilities that AWS is developing for the future. AWS commitment to pushing the boundaries of what's possible with Kubernetes continues to drive the roadmap. AWS is making continued investments in performance, resilience, and efficiency improvements. The architectural enhancements that enable 100,000 node support also provide a platform for future innovations that will make container orchestration even more powerful and efficient. This includes work on intelligent resource optimization, predictive scaling, and autonomous cluster management capabilities. Deeper integration with the comprehensive AWS cloud platform continues to be a key focus area. EKS Ultrascale doesn't exist in isolation. It's part of a broader ecosystem of AWS services that work together to enable next-generation applications. This includes tighter integration with AI/ML services, storage systems, networking capabilities, and security services. Most importantly, AWS is preparing for future AI workloads that we can barely imagine today. The pace of innovation in artificial intelligence continues to accelerate, and we are committed to ensuring that AWS provides the infrastructure foundation needed for whatever breakthrough comes next. Whether it's AGI systems, quantum classical hybrid computing, or entirely new paradigms we haven't yet conceived, EKS Ultrascale provides the scalable, reliable foundation that will enable these innovations. As we conclude today's comprehensive technical deep dive, I want to emphasize that Amazon EKS's support for 100,000 node clusters represents a fundamental breakthrough that enables the next generation of AI and ML applications. The architectural innovations we've discussed today, from etcd re-architecture to API optimizations to comprehensive testing validation, provide the foundation for unprecedented scale, while maintaining full Kubernetes conformance. For your next steps, I encourage you to contact your AWS account team for personalized guidance on how ultra-scale EKS can transform your AI/ML infrastructure. Our solution architects can help you evaluate how these capabilities align with your specific workload requirements and scaling plans. Start exploring how ultra-scale capabilities could revolutionize your AI/ML workloads. Whether you're training large language models, running distributed inference, or building the next generation of AI applications, ultra-scale EKS provides the infrastructure foundation you need. Begin planning your AI/ML infrastructure scaling strategy today. The future of AI requires infrastructure that can scale to meet the demands of increasingly sophisticated models and applications. With ultra-scale EKS, you are ready to build and deploy the AI applications that will define the next decade of innovation.